Tonight, we're going to work through one of the most deceptively simple questions in all of astronomy. How many stars are there? It sounds like the kind of question that should have a straightforward answer. Someone must have counted, someone must have added it up. It's not as though we're being asked to count something hidden or hypothetical. Stars are there, in the sky, night after night, doing nothing except producing light for billions of years. If anything should be countable, it's them. And yet, the actual number is unknown, not imprecise, not debated at the level of a few percent. Unknown in the sense that the leading estimates span a factor of 3 to 5, and the methods used to arrive at those estimates involve layers of inference, modeling, extrapolation, and assumption that would make a casual observer uncomfortable with how much is being calculated versus directly observed. The number of stars in the observable universe is not a measurement in any simple sense. It is a construction, an edifice built from a foundation of direct counts in the nearby solar neighborhood, extended outward through several different techniques, each of which introduces its own sources of uncertainty, to produce a final number that carries with it all of those uncertainties stacked together. The current best estimate is somewhere in the range of 10 to the 23rd to 10 to the 24th stars in the observable universe. That is a number between 100 sextillion and 1 sextillion multiplied by 1,000. Writing it out in digits would require writing a 1 followed by 23 to 24 zeros. The grains of sand on all Earth's beaches are estimated at roughly 10 to the 19th. There are roughly 100,000 to 1 million times more stars in the observable universe than grains of sand on Earth. And yet, this number, staggering as it is not known to better than about a factor of 3. Tonight's story is about how astronomers built that estimate from nothing, from counting a few thousand stars visible to the naked eye in ancient times, through the development of telescopic surveys and photometric catalogues, through the space-based missions that measured the distances to more than 1 billion stars with extraordinary precision, through the theoretical frameworks that allow us to extrapolate from measured samples to complete populations, and ultimately to the techniques that let astronomers count the integrated starlight from galaxies billions of light years away, and infer from that light how many individual stars produced it. By the end, you will understand not just what the number is, but why it is uncertain, what the specific sources of that uncertainty are, which of them could be resolved by future observations, and which are probably permanent features of the problem, and what it means that we can construct a reasonable estimate of something so impossibly large from the limited vantage point of one planet orbiting one star in one small corner of one ordinary galaxy. If this kind of deep look at how science actually works, not just what the science concludes, but how the conclusions were reached and why they carry the uncertainties they carry, is what you are here for, subscribe and leave a like. It genuinely helps this channel reach people who want the honest version of how we know what we think we know. Now, let's start with the most basic question of all. What exactly are we trying to count? The specific number that most people encounter when this question comes up, 100 billion stars in the Milky Way and 100 billion galaxies in the universe, was an estimate that circulated for decades and was based on relatively crude methods. That estimate, it turns out, was approximately right for the Milky Way, but significantly wrong for the number of galaxies. A 2016 analysis using deep Hubble observations and models of galaxy formation and evolution found that the number of galaxies in the observable universe is likely closer to 2 trillion than 100 billion. 2,000 times more galaxies than the standard figure that had been repeated for decades. If the galaxy count was that wrong, the stellar count built from it was also that wrong by the same factor. This revision illustrates something important about the stellar census. It is not static. It improves continuously as new observations become available and new analytical methods are applied. the history of the word. Question is a history of successive revisions, almost always upward, as each new generation of surveys reveals more objects that previous surveys missed. The universe consistently turns out to contain more of everything than we thought, because the things we missed are consistently the faint, the small, the distant, and the obscured. Tonight is about the methodology of the census, the actual physical and mathematical techniques that astronomers use to build this enormous number from scratch, starting with stars close enough to see individually, and scaling outward through the observable universe using every tool available. Before any counting can begin, the counting needs a definition. What is a star? The question seems trivial until you examine it carefully, at which point it turns out to be surprisingly nuanced, with specific physical thresholds that matter enormously for the census. The standard definition of a star is a body that sustains nuclear fusion in its core, at least at some point in its history. More specifically, the process that defines a star as genuinely stellar is the fusion of hydrogen into helium, the proton-proton chain, or the CNO cycle, both of which require a core temperature of roughly 10 to 15 million Kelvin and sufficient mass to create the gravitational pressure needed to achieve those temperatures. The minimum mass required to sustain hydrogen fusion is approximately 0.08 solar masses, or about 80 times the mass of Jupiter. Below this threshold, a body lacks the gravitational compression to heat its core to the fusion ignition temperature, and is not, in the strict technical sense, a star. This lower boundary matters enormously for counting stars, because the distribution of stellar masses is strongly weighted toward low masses. The most common stars in the universe are the least massive ones that still qualify. Red dwarf stars at the boundary of the fusion threshold, tiny compared to the Sun, dim to the point of invisibility to the naked eye even at modest distances, and yet present in such large numbers that they constitute the vast majority of all stars by count. Whether the census accurately captures these faint, low-mass objects determines whether the total stellar count is roughly correct or wildly wrong. The upper boundary of what counts as a star is less sharply defined. Stars above about 100 to 150 solar masses are thought to be unstable, unable to hold themselves together against the radiation pressure of their own luminosity. Such ultramassive stars have been observed, including R136A1 in the Large Magellanic Cloud, with an estimated mass approaching 200 solar masses. But they are extraordinarily rare, live only a few million years, and contribute minimally to the total star count despite their spectacularly disproportionate contributions to total stellar luminosity. The category that creates the most definitional difficulty is the brown dwarf. Brown dwarfs are bodies with masses between roughly 13 and 80 Jupiter masses. They are too massive to be planets in the conventional sense, but too light to sustain hydrogen fusion. Some brown dwarfs can briefly sustain deuterium fusion at their lowest mass range, and the most massive ones can sustain lithium burning, but they cannot sustain the proton-proton chain that defines true stellar status. Are they stars? Formally, no, but they exist along a continuous mass spectrum that transitions smoothly from stars to brown dwarfs to gas giant planets. And understanding where to draw the line affects every stellar census. For the purposes of tonight's discussion, we will count hydrogen-fusing objects as stars. Everything from 0.08 solar masses upward. We will return to the brown dwarf question later, because it has significant implications for what the total stellar count might be if the definition is adjusted. The transition between a star and a planet is also worth examining. The distinction between a star and a brown dwarf is the hydrogen fusion threshold at roughly 80 Jupiter masses. The distinction between a brown dwarf and a planet is less cleanly defined, but is often placed at the deuterium burning limit at about 13 Jupiter masses. Below this, bodies do not generate energy through any nuclear process, and are considered planets or planetary mass objects even when they float free in space unattached to any parent star. The planets in our own solar system have masses far below this limit. Jupiter, the most massive planet in the solar system, has a mass of about 318 Earth masses, roughly 1 Jupiter mass by definition, well below the 13 Jupiter mass deuterium burning threshold. For the stellar census, the critical question is how many objects exist near the hydrogen fusion threshold, in the range of 0.07 to 0.10 solar masses, where the distinction between a very dim red dwarf and a brown dwarf is made. Objects in this range are among the hardest to classify correctly because their spectroscopic signatures overlap, and their luminosities are too low for distance-limited surveys to detect them in large numbers. The completeness of the census in this mass range is a significant source of uncertainty in the total stellar count. One additional complication: a star is not always the same thing throughout its life. After exhausting its hydrogen fuel, a star transitions through a red giant phase and ultimately leaves behind a white dwarf. Is a white dwarf a star? By the strict definition of nuclear fusion, no. A white dwarf supports itself by electron degeneracy pressure rather than fusion. But it began its existence as a star, and the census of stellar remnants is part of the full picture of what the galaxy's stellar history has produced. The first star census in human history was performed with the naked eye, and it produced a number that remained essentially unchanged for roughly 2,000 years. The ancient Greek astronomer Hipparchus compiled a catalogue of approximately 850 stars around 129 BCE, assigning them positions and brightness rankings in a system of 6 magnitudes that forms the ancestor of the modern stellar magnitude scale. Ptolemy expanded this to approximately 1,022 stars in the Almagest around 150 CE. The Islamic astronomer al-Sufi refined and extended Ptolemy's catalogue in the 10th century, but the number remained in the same rough range. Under ideal dark sky conditions, the human eye with no optical aid can detect stars to about magnitude 6.5. The total number of stars in the entire sky visible to the naked eye under ideal conditions is approximately 9,096, though this varies somewhat depending on the specific cutoff used. Of these, roughly half are visible from any given point on Earth's surface at any given time, since the other half are below the horizon. On a typical clear night without exceptional darkness, a person might see 2,000 to 5,000 stars, depending on location and sky conditions. Ancient astronomers had no way to determine that these visible stars represented an extraordinarily tiny fraction of the total stellar population. There was no reason to suspect it. The stars visible to the naked eye looked distributed across the sky in a way that could plausibly represent the full extent of stellar creation. Many ancient cultures conceived of the fixed stars as a decorative canopy at a fixed distance from the Earth, a concept that required no deeper stellar census. The Greek philosophical tradition did produce the insight that the sun was probably a star similar to the others, but much closer, an idea advanced by Anaxagoras and later Aristarchus. This idea, correct as it was, took some time to gain traction and was not accompanied by any systematic attempt to estimate how many stars might lie at greater distances beyond the visible ones. What changed the picture was the telescope. Galileo turned a telescope to the Milky Way in 1609 and immediately discovered something the naked eye had never shown: the diffuse band of light that had been debated for centuries, interpreted as atmospheric phenomenon, fire, or cosmic river by various traditions, was composed of individual stars too faint and too numerous to be separated by unaided vision. The Milky Way galaxy revealed itself in the first night of telescopic observation as exactly what it is: a disk of stars so dense along our line of sight through the galactic plane that individual stars blur together into continuous light. This single observation shattered the idea that the naked eye census represented anything close to the total. The psychological and cultural significance of the visible sky is worth pausing on. For most of human history, the approximately 6,000 stars visible without optical aid on a good dark night represented the entirety of the known stellar universe. The specific number was close enough to countable that enumerating them was a practical task, and catalogues like those of Hipparchus, Ptolemy, and Al-Sufi represented genuine achievements of systematic observation. These astronomers knew the sky intimately and could identify individual stars by name and position, a kind of intimate familiarity with the stellar population that would become impossible once telescopes revealed that the true population was vastly larger. The invention of the telescope changed the relationship between humanity and the stellar census permanently. Galileo's observation of the Milky Way resolved it into stars, immediately suggesting that the galaxy contained far more stars than the few thousand visible to the eye. But even this recognition didn't produce any meaningful estimate of the total number, because there was no framework for determining the distances to most stars, and therefore no way to know how large the Milky Way was, or how densely populated. The first systematic attempt to map the Milky Way came from William and Caroline Herschel in the late 18th century. By counting stars in different directions across the sky, the Herschels attempted to infer the three-dimensional structure of the galactic system. Their method assumed that the apparent stellar density in each direction reflected the true depth of the galaxy in that direction, and that the Sun was near, the center of a flattened disk-like system. Their inferred map of the galaxy was roughly correct in shape, but wildly wrong in scale, partly because they had no way to account for the interstellar dust that made distant stars invisible in dusty directions. The most important obstacle to counting stars is not the number of them. It is the nature of the census required. There are roughly 2 trillion galaxies in the observable universe, each containing between 10 million and 1 trillion stars. The total number is so large that any direct count, even conceptually, is physically impossible. There are not enough time or computational resources in the universe to individually catalog each star, even if every star could somehow be individually resolved. The census must therefore be statistical, extrapolative, and built on frameworks that convert observable quantities into population estimates. Even within the Milky Way, the census problem is difficult in a specific way. The Milky Way contains somewhere between 100 and 400 billion stars, depending on which estimate you use. Astronomers have directly cataloged the precise positions and distances to approximately 1.5 billion of these using the Gaia satellite. That is a remarkable achievement, representing about 0.5% of even the lowest estimate of the total. The remaining 99+% must be inferred. The inference is not arbitrary. It rests on 2 foundational tools: the stellar luminosity function, which describes how stars are distributed across the range of intrinsic brightnesses, and the initial mass function, which describes how stars are distributed across the range of masses. Both of these have been measured from samples of nearby stars, with well-characterized distances and properties, and both can be integrated across a model of the galaxy structure to produce a total star count estimate. But both also carry significant uncertainties, particularly at the low mass end, where faint red dwarf stars are hard to detect. And both are model dependent in ways that introduce systematic errors. The scale problem becomes even more severe when moving beyond the Milky Way. Even the nearest large galaxy, Andromeda, at approximately 2.5 million light-years, cannot have its individual stars resolved and counted in any comprehensive way with current instruments. Astronomers can resolve and count individual stars in Andromeda's outer regions, but the dense central bulge remains unresolvable into individual stellar points at optical wavelengths. For galaxies at cosmological distances, individual stars are entirely unresolvable, and the stellar census must be performed entirely through the integrated light of all the stars in the galaxy considered together. The integrated light approach requires additional assumptions. Knowing the stellar populations present, their age and chemical composition distribution, their mass function, and how all of these translate into the total light observed. Each of these parameters introduces uncertainty. The total stellar count of the universe is therefore not a single measurement, but the result of propagating uncertainties through multiple layers of inference. And the final estimate carries error bars that span almost an order of magnitude. The statistical approach to the stellar census has a specific logical structure worth understanding. Direct counting, the method you would use to count objects in a jar or books on a shelf, requires that every individual object be individually identifiable. This is impossible for the stellar census even within our own galaxy, let alone across the observable universe. The alternative is to count in a complete sample of a smaller volume and then scale up to the total volume. This approach, called the volume complete sample method, requires defining a sphere around the Sun within which the census is essentially complete, meaning virtually every star within that volume has been detected and catalogued, and then using the measured stellar density within that sphere to calculate the expected total number of stars in a larger volume, applying corrections for the fact that the galaxy is not a uniformly dense sphere but has a complex three-dimensional structure. The practical limitation is that a truly complete census, one where even the faintest observable red dwarfs have been detected, can only be guaranteed within a few dozen light-years of the Sun. Within 25 light-years, roughly 100 star systems containing approximately 130 individual stars are catalogued, and the catalog is thought to be reasonably complete for all but the very faintest objects. Extending completeness to 50 or 100 light-years becomes progressively harder as the volume grows with the cube of the radius, and the census effort scales accordingly. The correction factors applied to extend the local census to the full galaxy are therefore built on relatively small, complete samples that are then extrapolated across a structure vastly larger than what was directly measured. Any systematic bias in the local sample, any type of star that is slightly underrepresented even within the volume where the census is claimed to be complete, propagates multiplicatively into the global estimate. The volume effect is one of the most critical yet underappreciated complications in the stellar census. If you imagine surveying the solar neighborhood in concentric shells of increasing radius, the number of stars in each shell grows with the square of the radius, while the volume grows with the cube. This means that more distant shells contain far more stars per unit thickness, but they are also far harder to survey completely. A survey that detects all stars within 30 light-years and half the stars within 300 light-years is dominated by the more distant, incomplete region simply because of the geometry. Getting the incomplete fraction right requires a careful model of how many stars at each distance were below the survey's detection limit, and this model is tied to the luminosity function of the stars being counted. The counts, the luminosity function, and the distance estimates are all entangled in a way that must be solved simultaneously rather than sequentially. Astronomers trying to map the Milky Way face a challenge that no other science confronts quite as directly. They are doing their cartography from inside the object being mapped. Understanding the structure of the Milky Way, including how many stars it contains, requires inferring the global properties of a system from a position embedded within it. It is somewhat like trying to draw a map of a forest from a location deep within the trees. The Sun is located approximately 26,000 light-years from the galactic center, in a spiral arm region called the Orion Arm or local spur. This is not particularly central, and it is not in the most star-dense part of the galaxy. From this vantage point, looking toward the galactic center, astronomers see the densest stellar region in the galaxy, but the view is heavily obscured by gas and dust in the galactic plane. The galactic center itself, dense with stars to an extraordinary degree around the central supermassive black hole, cannot be observed at optical wavelengths at all from Earth because of intervening dust. Infrared and radio observations pierce this dust and reveal the center, but converting those observations to a stellar census requires modeling the dust distribution and the conversion between infrared light and stellar population. Looking away from the galactic plane, the view is clearer. Stars in the galactic halo, the spheroidal component surrounding the disk, are visible with less dust absorption, but the halo is relatively sparsely populated compared to the disk, and halo stars contribute a small fraction of the total stellar count. The geometry of the galaxy creates additional complications. The spiral arms, which contain the most active star-forming regions and the most massive young stars, are traced by specific tracers. HII, regions ionized by hot young stars, molecular clouds where new stars are forming, certain types of variable stars with known intrinsic luminosities. But the spiral structure is not perfectly symmetric or regular, and mapping it from inside requires piecing together observations from many directions and distances. The galactic center region is also where the stellar density is highest. Within the central few hundred light years, the density of stars exceeds that of the solar neighborhood by factors of thousands to tens of thousands. Whether the stellar mass function in this extreme environment is the same as in the solar neighborhood is not certain, and variations in the mass function in different galactic environments add additional uncertainty to any global stellar count. Understanding the Milky Way's three-dimensional structure, the disk thickness, the bulge size, the warp and flare of the outer disk, and the density profile of the halo, is therefore prerequisite to integrating over the entire structure to get a total stellar count. All of these structural parameters are themselves measured with uncertainties, and those uncertainties propagate through to the final estimate. The rotation of the Milky Way provides one of the primary tools for mapping its structure from the inside. Stars, gas, and other matter orbit the galactic center at speeds that depend on the total mass distribution within the orbit. The Sun orbits the galactic center at roughly 220 kilometers per second, with an orbital period of approximately 225 to 250 million years. A period sometimes called a galactic year or cosmic year. Measuring the rotation velocities of objects at different galactic radii through Doppler shift measurements of their spectral lines provides information about the mass distribution, including the dark matter halo that dominates the total galactic mass. The spiral arm structure of the Milky Way has been one of the hardest features to establish because we cannot see the whole galaxy at once from inside it. The spiral arms were traced primarily through radio observations of the 21-centimeter emission from neutral hydrogen, which penetrates the galactic dust, and through observations of star-forming regions and young massive stars that concentrate in the spiral arms. These observations have revealed that the Milky Way is a barred spiral galaxy with a central elongated bar structure and 4 major spiral arms extending outward. The Sun sits between the inner Sagittarius Carina arm and the outer Perseus arm in a smaller feature called the Orion arm or Orion spur. Understanding the spiral structure is important for the stellar census because the arms are where star formation is concentrated. The stellar density in and near spiral arms is higher than in the interarm regions, and the population is on average younger and includes more massive stars. Any model that integrates stellar density over the full galaxy must correctly represent the arm to interarm contrast to get the total stellar count right. The stellar luminosity function is one of the foundational tools of the stellar census. It describes how many stars of each intrinsic brightness exist per unit volume of space. Plot the number of stars as a function of absolute magnitude, and you get a specific distribution curve that tells you how much of the galaxy's stellar population is concentrated at each luminosity level. The luminosity function has a specific and important shape. It rises steeply toward lower luminosities. There are far more faint stars than bright ones. A star 10,000 times brighter than the Sun is extremely rare. A star 1/100th as bright as the Sun is extremely common. This is not a coincidence or a curiosity. It reflects the underlying physics of stellar formation and evolution, specifically the initial mass function for star formation combined with the relationship between stellar mass and luminosity. Measuring the luminosity function requires knowing the distances to stars precisely enough to convert their apparent brightness, what we observe in the sky, into their intrinsic brightness, what they actually emit. For nearby stars, this is done through parallax measurements. The parallax of a star is the tiny shift in its apparent position against background stars as Earth moves around the Sun, and this shift is inversely proportional to the star's distance. Stars within a few hundred light years have parallaxes large enough to measure with ground-based telescopes. Stars out to a few thousand light years were measured with the Hipparchus satellite in the 1990s. The Gaia satellite has extended precise parallax measurements to distances of several thousand light years for the brightest stars and hundreds of light years for the faintest. The luminosity function of stars in the solar neighborhood has been measured with considerable precision. It rises steeply as luminosity decreases, with the faintest stars for which the function has been reliably measured, red dwarf stars at the bottom of the main sequence, outnumbering stars like the Sun by enormous factors. For every star as bright as the Sun, there are roughly 5 stars, somewhat less massive and less luminous. For every star like the Sun, there are perhaps 12 to 15 stars at 1/10 of solar luminosity. The function continues to rise as you go to lower luminosities, though it eventually turns over near the hydrogen fusion limit and the number of stars below that limit, the brown dwarfs, begins to fall. The luminosity function is the bridge between what we can observe, the apparent brightness distribution of stars in a survey, and what we want to know, the true distribution of stellar luminosities and therefore stellar numbers in a given volume of space. Applying it requires knowing the survey's completeness, how many stars of each type the survey would have detected, and correcting for the stars that were missed. The faint end of the luminosity function, where the count of stars per unit magnitude interval rises steeply, has been the subject of considerable investigation over the past few decades. The original luminosity function measurements, made from photographic surveys with limited faint limits, underestimated the steepness of the rise toward faint magnitudes because the surveys were incomplete at the faint end. Each generation of more sensitive surveys found more faint stars than the previous generation's luminosity function predicted, requiring upward revisions. The rise in the luminosity function at faint magnitudes has both observational and theoretical explanations. Observationally, faint stars are more numerous because of the shape of the stellar initial mass function. Low-mass stars are more common, and low-mass stars are less luminous, so the count per unit brightness interval increases as brightness decreases. Theoretically, stellar evolution models show that stars spend the majority of their lives on the main sequence, converting hydrogen to helium at roughly constant luminosity. So, the main sequence luminosity function reflects the initial mass function modified by the mass-luminosity relationship. One important subtlety in interpreting the luminosity function is the need to distinguish between the field star luminosity function, measured from stars distributed throughout the galactic disk, and the luminosity functions of star clusters. Star clusters, both open clusters of recently formed stars and globular clusters of ancient stars, have been heavily studied, and their luminosity functions are known in some detail. The cluster and field luminosity functions are not identical because different environments produce different mass functions, and because the evolutionary state of the stellar population differs. The connection between the luminosity function and the stellar initial mass function requires knowing the mass-luminosity relationship, how a star's luminosity depends on its mass. On the main sequence, this relationship follows a power law. Luminosity scales approximately as mass to the fourth power for stars more massive than the Sun, and as mass to the power of 2.5 or so for less massive stars. This steep mass-luminosity relationship means that small differences in mass produce large differences in luminosity, and the luminosity function therefore falls steeply toward bright stars, even though the mass function falls relatively gradually. Converting between the two requires precise knowledge of the mass-luminosity relationship, which is best measured from binary star systems, where both masses and luminosities can be determined. The stellar initial mass function, usually called the IMF, describes the distribution of stellar masses at birth. For every massive star born, how many intermediate mass and low mass stars are also born? This distribution has been measured from star-forming regions and young stellar clusters, and it has a characteristic shape that is now broadly accepted across many different stellar environments. The IMF, most commonly used, is the one derived by Edwin Salpeter in 1955, modified by subsequent work from astronomers, including Pavel Krupa and John Scalo. The Salpeter YMF is a power law. The number of stars formed with a given mass is proportional to that mass raised to a negative power of roughly 2.35. This means that for every star twice as massive as a reference mass, roughly 5 times fewer stars are born. For every star 10 times as massive, roughly 230 times fewer stars are born. This power law behavior means that the stellar population is completely dominated numerically by low-mass stars. The Sun is at approximately the median of the mass distribution in a solar-type neighborhood, meaning roughly half the stars are less massive. But the peak of the stellar number distribution is at masses considerably below the Sun, around 0.2 to 0.5 solar masses, and the tail toward lower masses continues almost to the hydrogen burning limit. The IMF matters enormously for the total stellar count, because counting light and counting stars are not the same thing. When astronomers look at a galaxy and measure its total luminosity, they are measuring the combined light of all its stars. But most of that light comes from the relatively few massive luminous stars, while the majority of stars by number are the faint, low-mass ones that contribute relatively little to the total light. Converting from total galaxy luminosity to total number of stars requires knowing the mass-to-light ratio of the stellar population, which in turn requires knowing the IMF. If the IMF is bottom-heavy, meaning more low-mass stars than the Krupa or Chabrier IMFs predict, then the mass-to-light ratio is higher than assumed, and the actual number of stars in the universe is larger than the luminosity-based estimates would suggest. Recent observations of massive elliptical galaxies have provided evidence that their IMF may indeed be more bottom-heavy than the solar neighborhood IMF, with a steeper rise toward low masses. If these elliptical galaxies, which contain a substantial fraction of the universe's total stellar mass, have significantly different IMFs from what local measurements suggest, the total stellar count could be larger than current estimates by a significant factor. The IMF is one of the dominant sources of systematic uncertainty in the global stellar census, and it is genuinely unknown whether the local IMF, measured in star-forming regions near the Sun, is universal across all galaxy types, all redshifts, and all environments. The specific form of the initial mass function at low masses has been a subject of sustained observational and theoretical effort. The high mass end, above a few solar masses, follows the Salpeter power law relatively well in most environments. The low mass end, below about 1 solar mass, shows a departure from the strict Salpeter form. the function flattens somewhat, rather than continuing to rise steeply, all the way to the hydrogen burning limit. This flattening means that the number of stars does not increase without bound toward ever lower masses, but instead approaches a turnover somewhere in the range of 0.2 to 0.5 solar masses. The precise location and shape of this low mass turnover is critical for the total stellar count because it determines how many red dwarf stars are produced for each more massive star. Variations in the turnover shape between different environments would produce variations in the mass-to-number conversion that affect the total stellar count of galaxies with different star formation histories. Theoretical models of the IMF attempt to explain its shape from first principles, starting from the physics of molecular cloud fragmentation and gravitational collapse. These models generally predict that there should be a characteristic mass below which the count of newly formed stars stops rising, because gas clouds below a certain mass cannot cool efficiently enough to form bound stellar objects. The gene's mass, which depends on the temperature, density, and chemistry of the gas, sets the scale for this characteristic fragmentation mass. However, getting from theoretical genes' mass estimates to specific IMF shapes requires additional physics, including turbulence, magnetic fields, radiation feedback, and the role of protostellar outflows, none of which are fully understood. Red dwarf stars, technically M-type main sequence stars, are the most common stars in the universe. They are also the hardest to count, the easiest to miss, and the ones whose total population is most uncertain. Understanding their demographics is central to any honest stellar census. Red dwarfs have masses ranging from about 0.08 to 0.6 solar masses and corresponding luminosities ranging from about 0.0001 to 0.04 solar luminosities. The least luminous red dwarfs at the hydrogen-burning minimum mass are approximately 10,000 times fainter than the Sun. A red dwarf at the mass of Proxima Centauri, 0.12 solar masses, has a luminosity of about 0.0017 solar luminosities. Proxima Centauri, the nearest star to the Sun, is completely invisible to the naked eye despite being only 4.24 light-years away. It requires a telescope to see it all. This invisibility has important consequences for the stellar census. Any survey that detects stars based on their observed brightness has a luminosity limit, a minimum detectable flux below which stars are lost. Because red dwarfs are so faint, they are lost from surveys at relatively small distances compared to brighter stars. A survey that can detect a sun-like star at 10,000 light-years can only detect the faintest red dwarfs at perhaps 50 light-years. The volume accessible for the census of faint stars is therefore enormously smaller than the volume accessible for bright stars. Correcting for this volume effect requires knowing the luminosity function precisely at low luminosities, which requires a complete census of faint stars in a well-defined volume nearby. The completeness of this census is itself uncertain. Even within 25 light-years of the Sun, new red dwarf and brown dwarf companions to known stars have been discovered relatively recently, suggesting that the catalog is not perfectly complete even at this tiny scale. Each discovery of a missed faint star in the solar neighborhood adjusts the inferred number of faint stars per unit volume, which propagates upward to revise the total galactic stellar count. The significance of red dwarfs for the total stellar count is extreme. If you count only stars visible to the naked eye, you miss roughly 99.9% of all stars. If you count all stars detected in an optical survey of the entire sky to reasonable depth, you still miss the majority of M dwarfs in the galaxy. The counting problem for red dwarfs is not merely one of faint stars being harder to observe. It is one where the counting incompleteness is so severe that the correction factor applied to obtain the total count from the observed count is a large number subject to significant uncertainty. Current estimates suggest that M-dwarf stars constitute roughly 70 to 75% of all stars in the Milky Way by number, and probably a similar fraction in the universe as a whole. Getting this fraction right is essential for any honest accounting of the cosmos's stellar population. The discovery of new red dwarf neighbors to the Sun has not slowed down in recent years. As infrared surveys have become more sensitive and as proper motion catalogues have improved, new very low-mass stars and brown dwarfs have been found at distances of only a few light-years, close enough that they should have been obvious in prior surveys. WISE J 104915.57 -53190 6.1, discovered in 2013 and informally called Lumen 16, is a binary pair of brown dwarfs at only about 6.5 light-years from the Sun, making it the third closest known stellar system after Alpha Centauri and Barnard's star. Its discovery in relatively recent years illustrates that even within a few light-years of the Sun, the census of faint objects is not fully complete. The astrobiological implications of the red dwarf majority are worth noting in the context of a stellar census. Because red dwarfs are so much more numerous than Sun-like stars, and because red dwarf lifetimes are extremely long, ranging from tens of billions to over 1 trillion years for the least massive ones, if planetary systems around red dwarfs are potentially habitable, then the vast majority of potentially habitable planets in the universe orbit red dwarfs. The stellar census connects directly to the question of the cosmic distribution of life through the dominance of red dwarfs in the stellar population. Current surveys of red dwarf planetary systems, including results from the TRAPPIST telescope and the Transiting Exoplanet Survey satellite, have found that red dwarfs very commonly host planets, and that many of these planets are in the habitable zone where liquid water could exist. Whether the hostile aspects of red dwarf environments, particularly the stellar flares that bombard close-in planets, prevent or permit life is one of the most actively researched questions in astrobiology. Any stellar census rests on a foundation of known distances. Without distances, apparent brightness cannot be converted to intrinsic luminosity. Stars cannot be placed in their correct positions in the galaxy, and the volume surveyed for any given type of star cannot be calculated. Distance measurement is the bedrock of stellar astronomy. The most fundamental distance measurement technique is trigonometric parallax. As Earth moves around the Sun over the course of a year, nearby stars appear to shift position relative to more distant background stars. This shift, measured in arcseconds, is called the parallax, and the distance in parsecs is simply 1 divided by the parallax in arcseconds. A star with a parallax of 1 arcsecond is at a distance of 1 parsec, approximately 3.26 light-years. A star with a parallax of 0.01 arcseconds is at 100 parsecs, approximately 326 light-years. The challenge is that even nearby stars have tiny parallaxes. Proxima Centauri, the nearest known star, has a parallax of 0.77 arcseconds, the largest parallax of any star. As distance increases, parallax decreases, and eventually the parallax signal becomes too small to measure reliably against the noise of the measurement. From the ground, atmospheric distortion limits parallax precision to about 10 to 20 milliarcseconds, allowing reliable distances to perhaps a few hundred light-years for typical measurements. The Hipparchus satellite, launched by the European Space Agency in 1989, measured parallaxes from space with a precision of about 1 milliarcsecond, extending reliable distance measurements to about 1,600 light-years for bright stars. Hipparchus measured distances to roughly 120,000 stars with reasonable precision and to a larger catalog of over 1 million stars with lower precision. This was transformative for stellar astronomy and provided the framework for much of the luminosity function work that followed. The Gaia satellite, launched in December 2013, operates from the L2 Lagrange point and achieves parallax precisions of roughly 20 to 30 microarc seconds for bright stars, a factor of 50 times better than Hipparchus. By its most recent data release, Gaia has measured parallaxes for approximately 1.5 billion stars with useful precision, with distance uncertainties of roughly 1% for nearby stars, and growing to larger fractional uncertainties at greater distances. For the first time in history, the three-dimensional positions of a substantial fraction of the Milky Way's nearby stellar population are known. The Gaia parallax catalog is the most direct, measured contribution to the stellar census. For stars within a few thousand light-years of the Sun, we have actual measured distances for a large fraction of the observable population. The parallax technique becomes insufficient for stars at distances beyond several thousand light-years, where the parallax angle becomes too small to measure reliably even from space. For stars at greater distances, astronomers rely on a variety of secondary distance indicators that have been calibrated against parallax measurements for nearby objects where direct distance measurement is possible. Spectroscopic parallax, somewhat confusingly named, since it does not measure actual parallax, involves classifying a star's spectral type and luminosity class from its spectrum, using the known luminosity of stars in each classification to determine the star's intrinsic brightness, and then comparing this intrinsic brightness to the observed apparent brightness to infer the distance. This method has much larger uncertainties than trigonometric parallax, typically 20 to 30% for individual stars, but can be applied to stars at any observable distance. Cepheid variable stars provide a more precise secondary distance indicator. Cepheids are luminous pulsating stars whose pulsation period is tightly correlated with their intrinsic luminosity, a relationship discovered by Henrietta Swan Leavitt in 1908. By measuring the period of a cepheid and reading off its intrinsic luminosity from the period luminosity relation, then comparing to the observed brightness, the distance can be determined to about 5 to 10% precision. Cepheids are visible at distances of tens of millions of light-years in nearby galaxies, bridging the gap between the nearby universe where parallax works and the distant universe where only integrated galaxy properties are observable. The calibration of each secondary distance indicator against trigonometric parallax for nearby representatives of the same class is what converts them from relative to absolute distance measures. The Gaia mission has enormously improved these calibrations by providing parallaxes for large numbers of Cepheids, red giants, and other stellar types used as distance indicators, reducing the systematic errors in the distance scale that propagate into all stellar census estimates. The concept of the distance ladder captures the hierarchical structure of cosmic distance measurement. Each rung of the ladder calibrates against the rung below it, propagating knowledge of distances outward from the solar neighborhood to the observable universe. The first rung is trigonometric parallax, directly measuring distances to nearby stars. The second rung uses stellar parallaxes to calibrate spectroscopic and photometric distance indicators. The third rung uses Cepheids and other variable stars calibrated by nearby parallaxes to reach nearby galaxies. The fourth rung uses supernovae and other luminous standard candles in nearby galaxies to extend to cosmological distances. Each rung introduces additional calibration uncertainty, and the cumulative uncertainty of the full distance scale is one of the most actively debated topics in modern cosmology. Between the earliest naked-eye catalogs and the Gaia mission's billion-star parallax survey lies a long history of photometric surveys that progressively expanded the known stellar population. Understanding this history illuminates how the census has been built, the techniques used, and the limitations of each approach. Photometry, the measurement of the brightness of stars in specific wavelength bands, is the workhorse technique of the stellar census. By measuring a star's apparent brightness in multiple wavelength bands, astronomers can classify its spectral type, which correlates closely with its surface temperature and mass, and can estimate its distance using spectrophotometric methods. Spectrophotometric distances are not as precise as parallax distances, but can be applied to far more stars at far greater distances. The Palomar Sky Survey, beginning in the 1950s, was among the first systematic photographic surveys to cover the entire northern sky to substantial depth, detecting stars to roughly 20th magnitude. This was roughly 6 magnitudes fainter than the naked eye limit, corresponding to a factor of 250 in apparent brightness. Subsequent generations of digital surveys replace photographic plates with electronic detectors, dramatically improving measurement precision and enabling automated star detection. The Sloan Digital Sky Survey, which began operations in 2000 and has continued with successive phases through to the present, is one of the most comprehensive stellar catalogues available. It has imaged roughly 35% of the sky in 5 photometric bands and obtains spectra of millions of objects. The photometric catalog contains over 1 billion detected objects, though the great majority of these at the faint end are galaxies rather than individual stars. For stellar astronomy, the SDSS provides photometry for several 100 million stars to magnitude limits of about 22 in the most sensitive bands. The 2-micron all-sky survey, completed in 2001, observed the entire sky in 3 near-infrared wavelength bands. Infrared surveys are particularly important for the stellar census because dust in the galactic plane absorbs and scatters blue light much more effectively than red and infrared light. An infrared survey can therefore see through dust that obscures optical surveys, penetrating the galactic plane and allowing census work in regions invisible to optical telescopes. Each successive generation of survey has added to the stellar catalog in 2 complementary ways: by going to fainter limits and finding more stars at greater distances, and by improving measurement quality for stars already known, reducing the classification errors that contaminate census estimates. The progression from photographic plates to digital detectors to space-based survey satellites like Gaia represents a continuous improvement in both depth and precision. The development of charge-coupled devices in the 1970s and 1980s transformed observational astronomy by replacing photographic plates with electronic detectors. CCDs offered advantages in linearity, dynamic range, and sensitivity that dramatically improved photometric precision. A modern astronomical CCD can measure the brightness of a star to a precision of better than 1%, in seconds of exposure, time that would have required hours on a photographic plate, and the resulting measurements are immediately digital and amenable to automated analysis. The combination of large telescope fields of view, high-sensitivity CCDs, and automated data processing pipelines has made possible surveys that would have been literally inconceivable to astronomers of previous generations. The Dark Energy Survey, which operated from 2013 to 2019 using a 570 megapixel camera on a 4-meter telescope in Chile, imaged 5,000 square degrees of sky to extraordinary depth, detecting hundreds of millions of galaxies and hundreds of millions of stars with precise multi-band photometry. Surveys like this generate data products measured in petabytes and require purpose-built software to extract stellar catalogs. The Legacy Survey of Space and Time, planned for the Vera C. Rubin Observatory, currently being commissioned in Chile, will survey the entire southern sky every few nights for 10 years with a 3.2 gigapixel camera, generating about 15 terabytes of data per night and producing by the end of the survey a catalog of approximately 37 billion sources. This will include approximately 10 billion stars in the Milky Way, and Magellanic Clouds, detected repeatedly over the 10-year baseline. The repeated observations will reveal variable stars, proper motions, and parallaxes for relatively nearby bright stars, adding another layer to the stellar census and providing new constraints on the completeness of existing catalogs. The Gaia mission of the European Space Agency represents the most ambitious stellar census project in history and has transformed our understanding of the Milky Way's stellar population in ways that will take decades to fully process. Launched in December 2013 and placed in an orbit around the Sun-Earth, L2 Lagrange point, Gaia has been continuously scanning the sky with 2 optical telescopes, precisely measuring the positions, motions, and brightnesses of every star it observes. Gaia's primary mission objective is astrometry, the precise measurement of stellar positions and motions. By measuring the same stars repeatedly over a multi-year mission, Gaia builds up precise parallax measurements from the accumulated positional data. The repeated measurements also reveal proper motions, the slow drift of nearby stars across the sky due to their physical motion through the galaxy. And for a large subset of stars, bright enough to obtain useful spectra, Gaia measures radial velocities, the component of stellar motion toward or away from the Sun. The combination of position, parallax, proper motion, and radial velocity gives a complete 6-dimensional view of the kinematic state of each cataloged star, where it is and how it is moving. This information feeds into models of the Milky Way's structure and dynamics and allows astronomers to probe the mass distribution of the galaxy, including the dark matter content, with unprecedented precision. The Gaia Data Release 3, published in 2022, contains astrometric solutions for approximately 1.5 billion sources, spectroscopic information for 220 million sources, and astrophysical parameters for hundreds of millions of stars. The catalog is essentially complete to about magnitude 19 for the full sky, meaning it contains virtually every star brighter than that limit. For fainter stars, the catalog becomes increasingly incomplete, but even at the faint limit, there are significant numbers of nearby red dwarf stars captured. What Gaia has revealed about the Milky Way goes well beyond simply counting stars. It has shown that the galactic disk was disturbed by the passage of the Sagittarius dwarf galaxy, which is currently being disrupted and absorbed by the Milky Way, creating ripples in the stellar distribution that persist as observable kinematic substructure. It has revealed multiple major accretion events in the Milky Way's history, identified by the specific orbital characteristics of stars whose host galaxies were swallowed long ago. It has precisely mapped the distribution of open clusters and moving groups, and has identified structures in the Milky Way's disk that no previous survey had detected. For the stellar census specifically, Gaia provides the most reliable baseline population for nearby stars from which corrections to the total galactic count can be calculated. Within several hundred parsecs, the catalog is approaching completeness for all but the very faintest red dwarfs, providing a solid foundation for extrapolation to the full galaxy. The Gaia data have also revealed that the Milky Way has a richer and more turbulent merger history than previously known. By identifying stars with similar orbital characteristics and chemical compositions, but distinct from the typical stellar population of the galactic disk, astronomers have identified several past merger events where smaller galaxies or globular cluster systems were absorbed by the Milky Way. The most significant of these identified merger events, now called the Gaia Sausage Enceladus event, is thought to have occurred roughly 8 to 11 billion years ago, when the Milky Way absorbed a galaxy of several billion solar masses. Stars from this absorbed galaxy now populate the interstellar halo, with a characteristic elongated distribution in velocity space, hence the sausage nickname. This merger history has implications for the stellar census because the absorbed stars represent a component of the total stellar population that had a different formation history from the Milky Way's own stellar disk. Understanding the mass budget of the various merger events, including how many stars they contributed, is part of reconstructing the full stellar count and understanding how the Milky Way assembled its current stellar population over cosmic time. The proper motion measurements from Gaia have also revealed the three-dimensional kinematics of open clusters, star-forming associations, and moving groups throughout the galactic disk. These kinematic data allow the identification of co-moving groups of stars that formed from the same molecular cloud, tracing back the shared origins of stars now distributed over significant distances. This information helps constrain the stellar initial mass function as observed in real star-forming environments and provides tests of theories of how star formation proceeds in molecular clouds. The accuracy of Gaia's parallax measurements depends on the ability to establish a rigid, non-rotating reference frame against which stellar positions can be measured. Gaia uses the positions of distant quasars, extremely luminous objects at cosmological distances, whose positions are effectively fixed on the sky, because any proper motion due to their distance would be undetectable, as reference points for this inertial frame. The quasar reference frame is tied to the International Celestial Reference Frame, which has been maintained using very long baseline interferometry radio observations for decades. Gaia's alignment to this reference frame ensures that the parallax measurements are not affected by systematic rotations of the measurement coordinate system. For the overwhelming majority of galaxies in the observable universe, individual stars cannot be distinguished. The stars blur together at cosmological distances into the integrated light of the whole galaxy, which appears as a smear of photons in the detector. The stellar census of these galaxies must be performed by analyzing this integrated light using what astronomers call spectral energy distribution, modeling, or stellar population synthesis. The technique works as follows. A galaxy's total light output is measured in many different wavelength bands, from ultraviolet through visible to infrared. The shape of this energy distribution, how the light is distributed across wavelengths, encodes information about the stellar populations present. A galaxy dominated by young, hot, massive stars emits relatively more ultraviolet light. A galaxy dominated by old, cool, low-mass stars emits relatively more red and infrared light. A galaxy with a complex mix of stellar ages and masses produces a spectral energy distribution that is a linear combination of contributions from each stellar type. Stellar population synthesis models provide theoretical spectra for stellar populations of different ages, chemical compositions, and mass functions. By fitting the observed spectral energy distribution of a galaxy to a combination of these models, astronomers can estimate the mix of stellar populations present, and from that estimate, the total stellar mass. The stellar mass is then converted to a stellar number, using assumptions about the mass function. The conversion from spectral energy distribution to stellar mass involves several sources of uncertainty. The contribution of dust, which absorbs light at short wavelengths and re-emits it at longer wavelengths, must be modeled. The metallicity of the stellar population, its chemical composition, affects the colors of stars in complex ways that are degenerate with age effects. The form of the initial mass function, particularly its behavior at low masses, is uncertain and has a large effect on the resulting stellar count. Galaxies also contain stars in widely different evolutionary states. Main sequence stars, red giants, horizontal branch stars, asymptotic giant branch stars, planetary nebulae, white dwarfs, and others. Each of these stages contributes differently to the integrated light and must be correctly represented in the population synthesis models. Modern models have become increasingly sophisticated, but the fundamental degeneracies inherent in fitting integrated light mean that stellar masses from this method carry uncertainties of at least 30 to 50% for individual galaxies. The photometric approach works well for individual galaxies observed in isolation, but many galaxies in the universe are in dense environments, clusters and groups where galaxies are crowded together, and where the stellar populations of different galaxies can overlap in projection. Separating the stellar contributions of individual galaxies in a crowded cluster environment requires additional techniques, including detailed modeling of the spatial distribution of light and statistical decomposition of the integrated spectral signals. Galaxy clusters also contain a diffuse component of stars that are not associated with any individual galaxy, but float freely in the intracluster medium, stripped from galaxies by gravitational interactions. This intracluster stellar population can contribute a substantial fraction of the total stellar mass in clusters, ranging from roughly 10 to 50% depending on the cluster richness and history. These stars are extraordinarily difficult to detect because they are diffuse and scattered, and they must be accounted for in any complete census of the stellar population of galaxy clusters. At very high redshifts corresponding to the first few billion years of cosmic history, galaxy morphologies are irregular, and the stellar population synthesis models are less well calibrated because the stellar populations themselves are younger and more homogeneous than in the nearby universe. The James Webb Space Telescope has made significant contributions to understanding stellar populations in high redshift galaxies, detecting rest frame optical emission that with Hubble would have been redshifted into the infrared and undetectable. JWST's observations of early galaxies have found that some were surprisingly mature and massive for their early cosmic age, challenging models of galaxy formation and potentially affecting estimates of how much of the universe's total stellar mass was already in place at early times. The systematic uncertainties in spectral energy distributions fitting have motivated complementary methods of estimating stellar masses. One important alternative is dynamical mass estimation, in which the measured velocities of stars or gas in a galaxy are used to determine the total mass through the virial theorem or through detailed dynamical models. Dynamical masses measure total mass, including dark matter, but subtracting a model-dependent dark matter contribution gives the stellar mass. Agreement between photometric and dynamical stellar mass estimates provides confidence that the methods are not wildly inconsistent. Stars and galaxies are not a uniform population. They form continuously over time, or in some galaxies in intense bursts, and different generations of stars have different properties. Understanding the concept of stellar populations is essential for correctly interpreting the integrated light of galaxies, and for understanding what the total stellar census is actually counting. The concept of stellar populations was introduced by the German-American astronomer Walter Baade during World War II, when he used the newly built 100-inch telescope at Mount Wilson in a Los Angeles blacked out due to wartime restrictions to resolve individual stars in Andromeda's central bulge for the first time. He noticed that these stars were different in color and character from the stars in Andromeda's spiral arms, and he coined the terms Population 1 and Population 2 to describe the two groups. Population 1 stars are relatively young stars found in the disks of spiral galaxies, particularly in and near the spiral arms where star formation is ongoing. They are chemically enriched, meaning they contain significant amounts of elements heavier than hydrogen and helium, which astronomers call metals. This enrichment comes from previous generations of stars that synthesized heavy elements in their interiors and scattered them through supernova explosions and stellar winds. The Sun is a Population 1 star, relatively metal-rich and formed about 4.6 billion years ago. Population 2 stars are older stars found in the bulges and halos of galaxies and in globular clusters. They formed earlier in the universe's history when the available interstellar material had been less chemically enriched by previous stellar generations. Population 2 stars are metal poor compared to population 1, often by factors of 10 to 1,000 or more. The oldest population 2 stars have ages of 12 to 13 billion years and were among the first stars to form after the Big Bang. A hypothetical population 3, the very first generation of stars, would have formed from gas that was essentially pure hydrogen and helium, with essentially no heavy elements. No population 3 stars have been directly detected, though there are candidates because they would have been very massive, very hot, very luminous, and very short-lived, burning through their hydrogen fuel in perhaps 1 million years. Their contribution to today's total stellar count is effectively zero because they are all dead, but they contributed to the chemical enrichment of the universe that made all subsequent stellar generations possible. For the stellar census, the distribution of stellar populations matters because different populations have different mass functions, different age distributions, and different ratios of evolved to main sequence stars. A galaxy with a large old stellar population has a different mass-to-light ratio from a galaxy with ongoing star formation, and applying the wrong conversion factor when estimating stellar masses from luminosities leads to systematic errors in the total star count. The concept of stellar populations has been refined since Bade's original formulation to incorporate a more continuous spectrum of stellar ages, metallicities, and kinematic properties. Modern stellar population studies recognize that the distinction between population 1 and population 2 is oversimplified. There is a continuous distribution of stellar ages and chemical compositions, reflecting the continuous history of star formation and chemical enrichment in the galaxy. The alpha to iron ratio is an important diagnostic of stellar population age. Alpha elements, those with masses that are multiples of the helium-4 nucleus, including oxygen, magnesium, silicon, and calcium, are produced predominantly by core collapse supernovae, which explode within a few million years of massive star formation. Iron is produced primarily by type 1a supernovae, which are binary star systems that explode on longer time scales of several hundred million to several billion years after star formation. Stars that formed early in the galaxy's history, when the interstellar medium had been enriched primarily by core collapse supernovae, have high alpha to iron ratios. Stars formed later, after the iron-producing type 1a supernovae have had time to contribute their products, have lower alpha to iron ratios. This chemical clock connects to the stellar census through the age-metallicity relation. By measuring the just chemical compositions of large samples of stars in different galactic environments, astronomers can reconstruct the star formation history and understand how the stellar population was assembled over time. The Milky Way's stellar disk appears to have had 2 main phases of star formation: a thick disk formed early with high alpha to iron ratios, and a thin disk formed over a longer period with lower alpha to iron ratios. And this 2-component structure is visible in the chemical abundance distributions of disk stars measured by large spectroscopic surveys like APOG and Gaia. Perhaps the most important systematic limitation in the stellar census is interstellar dust. The space between stars is not truly empty. It contains gas and tiny solid particles, typically called dust, though they are more like smoke particles or soot, consisting primarily of silicates and carbonaceous compounds mixed with various other materials. This dust absorbs and scatters light, particularly at ultraviolet and optical wavelengths. A beam of visible light can be significantly attenuated even by modest columns of interstellar dust, and in the densest regions of the galactic plane, the extinction can be severe enough to make optical observation essentially impossible. The consequences for the stellar census are significant. Looking through the galactic plane in the direction of the galactic center, The dust extinction is so severe that optical surveys can barely penetrate a few thousand light years before losing essentially all their signal. The galactic center itself, at roughly 26,000 light years, is completely invisible at optical wavelengths. Radio and infrared observations pierce the dust and reveal the dense stellar regions near the center. But converting infrared observations to a stellar census requires knowing the dust column density precisely enough to correct for its reddening and attenuation effects. The infrared correction is not a small correction. For sightlines through the galactic plane, the dust extinction at optical wavelengths can correspond to factors of 10 to 100 or more in light attenuation. A star that would be observed at magnitude 15 in the absence of dust might be observed at magnitude 25 through a typical dusty galactic plane sightline, effectively making it invisible to surveys that only reach magnitude 22 or 23. The correction brings back stars that were hidden, but the correction depends on a dust model that is not perfectly known. The three-dimensional distribution of dust in the Milky Way has been mapped with increasing precision, using a combination of stellar photometry and reddening measurements. Dust reddens starlight, making stars appear redder than their intrinsic color. And this reddening can be measured for large samples of stars to map where the dust is concentrated. Three-dimensional dust maps based on surveys of millions of stars now provide spatial resolution of a few parsecs in well-observed regions and allow astronomical surveys to estimate how many stars are hidden behind given dust columns and therefore how much to correct the observed stellar counts. The stars in the most heavily obscured regions of the galaxy near the galactic center and in dense molecular clouds throughout the galactic plane represent a correction to the total stellar count that is estimated from models rather than from direct observation. This systematic uncertainty is one of the reasons the total stellar count for the Milky Way spans a range from roughly 100 billion to 400 billion stars, depending on the estimate. The total column of dust toward the galactic center has been estimated at approximately 30 magnitudes of extinction at visual wavelengths, meaning that the brightness of the galactic center as seen in visible light is reduced by a factor of about 10 to the 12th, equivalent to making it 1 trillion times fainter than it would appear without dust. No optical telescope could ever directly image a star in the galactic center, even with perfect instrument sensitivity, because there are simply too few photons arriving at any given collecting area. Infrared and radio wavelengths suffer far less extinction, with the same dust column producing only a few magnitudes of attenuation at 2 microns in the near infrared, and essentially none at radio wavelengths. The WISE All-Sky Infrared Survey, completed in 2012, and the ongoing NEO-WISE extension have provided full-sky infrared photometry that penetrates the galactic dust far more effectively than any optical survey. The 2-micron all-sky survey and the UK IRT infrared deep sky survey have provided even deeper infrared catalogues of specific regions. These surveys reveal a stellar population in the inner galaxy that is largely invisible to optical surveys, adding stars to the census that would otherwise be missing. The correction from infrared observations to a complete stellar count requires knowing the dust temperature and composition, because different dust properties produce different extinctions at different infrared wavelengths. The three-dimensional distribution of dust must also be modeled accurately to correct properly for each star's location within the dust column. Modern dust maps based on Gaia and infrared photometry of hundreds of millions of stars have reached parsec scale resolution in the solar neighborhood, and progressively coarser resolution at greater distances. The stellar census of the observable universe requires scaling up from individual galaxies to the full population of roughly 2 trillion galaxies, each with its own stellar content. This scaling step introduces additional layers of uncertainty, but also draws on some of the most powerful observational tools in modern astronomy. The galaxy census itself has been assembled over decades through photometric redshift surveys, spectroscopic surveys, and more recently through deep imaging with the Hubble Space Telescope and its successors. The Hubble Ultra Deep Field, a 9-day continuous exposure of a region of sky covering about 1/13 millionth of the total celestial sphere, revealed approximately 10,000 galaxies in that tiny patch. Extrapolating to the full sky gives roughly 100 billion galaxies in the observable universe accessible to Hubble's depth. More recent analyses using image reconstruction techniques suggest this number may be closer to 2 trillion when accounting for galaxies too faint to have been detected even by Hubble. Each of these galaxies has a total stellar mass, estimated from its luminosity and stellar population, using the methods described in earlier chapters. The stellar mass function of galaxies, which describes how many galaxies there are at each total stellar mass, has been measured from multiple surveys and shows that the majority of cosmic stellar mass is contained in massive elliptical galaxies, which formed most of their stars in a vigorous burst in the first few billion years after the Big Bang, and have been relatively quiescent since. Multiplying the stellar mass function by the mass-to-number conversion for each galaxy type gives the total stellar count of the observable universe. This calculation has been performed by several groups using different methods and with different assumptions, and the results consistently cluster around a few times 10 to the 23rd to a few times 10 to the 24th stars. The answer also depends on what epoch of the universe's history is being counted. The observable universe today contains the stars that currently exist. Some fraction of all stars ever formed have already died as white dwarfs, neutron stars, or black holes. A census of all stars that have ever existed, including the dead ones, would produce a different and larger number. Tonight's count is about currently living stars, those actively fusing hydrogen, plus the evolved stars that have not yet ended their lives entirely. The galaxy count itself has been refined by increasingly deep surveys. The classical estimate of roughly 100 billion galaxies in the observable universe rested on observations with Hubble that could detect galaxies to approximately magnitude 30 in the deepest fields. A 2016 reanalysis by Christopher Consolis and colleagues used data from multiple deep fields and applied a correction for the galaxies that were present at early cosmic times but have since merged with larger galaxies. This correction, based on models of galaxy mergers, suggests that the number of galaxies in the observable universe is closer to 2 trillion, roughly 20 times the previous estimate. Whether to count 2 trillion galaxies or 100 billion galaxies makes a substantial difference to the total stellar count, and both the correction methodology and the merger modeling required are sources of uncertainty. The resolution of this question requires deep surveys at higher redshifts than Hubble could achieve, which is why the James Webb Space Telescope's observations of the early universe are important for refining both the galaxy count and the stellar population of early galaxies. The distribution of stellar mass across galaxy types and sizes also matters for the total count. Not all galaxies contain the same number of stars per unit mass, because different galaxy types have different stellar populations, and therefore different mass-to-light ratios and mass-to-number ratios. Dwarf galaxies, which are vastly more numerous than massive galaxies, contain far fewer stars per galaxy, and tend to have younger stellar populations with higher mass-to-light ratios than giant ellipticals. Properly accounting for the contribution of dwarf galaxies to the total stellar census requires extending the galaxy's stellar mass function to very low masses. The contribution of satellite galaxies and dwarf galaxies to the total stellar count deserves specific attention. Large galaxies like the Milky Way are surrounded by populations of satellite dwarf galaxies, some containing only millions of stars. The Milky Way has dozens of known satellite galaxies ranging from the large and small Magellanic Clouds, with billions of stars, to ultra-faint dwarf galaxies containing only a few thousand stars. If large galaxies universally host such populations of satellites, the total number of dwarf galaxies in the universe substantially exceeds the number of larger galaxies, though their individual stellar contributions are small. Understanding how many stars exist today requires understanding how they came to exist over the history of the universe. The cosmic star formation history, the rate at which new stars have been born per unit volume of space as a function of cosmic time, is one of the most important observational constraints on models of galaxy formation and evolution. The cosmic star formation rate density has been measured across a wide range of redshifts using multiple observational tracers. Ultraviolet luminosity traces recently formed massive stars that emit copiously in the ultraviolet. Infrared luminosity from galaxies with active star formation traces the ultraviolet that has been absorbed by dust and re-emitted at longer wavelengths. Hydrogen emission lines and galaxy spectra trace regions of ionized gas surrounding hot young stars. All of these tracers give consistent results when properly calibrated. The picture that emerges is one of dramatic variation. The cosmic star formation rate was very low in the first few 100 million years after the Big Bang, when the first stars and galaxies were forming. It then rose steeply, reaching a peak around 10 billion years ago, when the universe was roughly 3 billion years old. This era of peak star formation, sometimes called cosmic noon, saw the universe forming stars at a rate roughly 10 times higher than the current rate. Since then, the cosmic star formation rate has been declining, falling to its current level, which is perhaps 10 to 30 times below the peak. The implications for the current stellar census are significant. Most stars alive today formed more than 5 billion years ago, before the dramatic decline in cosmic star formation. The stars being born today represent a relatively small addition to the cosmic stellar inventory, compared to what was accumulated during the peak era. The older stars formed during cosmic noon are predominantly the low-mass red dwarfs and intermediate-mass stars that still exist today, while the massive stars born during that same era have long since died in supernova explosions. The decline in cosmic star formation is connected to the depletion of cold gas in galaxies. Star formation requires cold, dense molecular hydrogen clouds, and these clouds are progressively consumed by star formation and depleted by feedback from stellar winds, supernova explosions, and active galactic nuclei. As galaxies age, they become increasingly gas-poor and correspondingly star formation poor. This means that the current epoch is one of waning stellar creation, and the total stellar population will eventually peak and then slowly decline as stars die faster than new ones are born. The peak cosmic star formation rate around 10 billion years ago produced most of the stars we see in the universe today. Integrating the cosmic star formation rate density over time gives the total stellar mass ever formed in a given volume of the universe, accounting for the fact that many of the stars formed early have since died. The current stellar mass density of the observable universe is estimated at roughly 10 to the 9 solar masses per cubic megaparsec, representing the integrated result of 13 billion years of cosmic star formation minus the mass returned to the interstellar medium when stars died. The decline in cosmic star formation since cosmic noon is connected to the role of active galactic nuclei. When a supermassive black hole at the center of a massive galaxy is actively accreting material and producing an active galactic nucleus, the enormous energy output can heat the surrounding gas, drive galactic winds, and suppress star formation throughout the galaxy. This AGN feedback mechanism is thought to be responsible for transforming blue, star-forming galaxies into red, passive galaxies, a transition that occurred predominantly between about 5 and 10 billion years ago when the universe's most massive galaxies exhausted their star formation activity. The history of cosmic star formation matters for the stellar census, not only because it determines how many stars exist today, but because it constrains the age distribution of the stellar population. Most stars today are more than 5 billion years old, formed during or before the era of peak cosmic star formation. The young stellar population, those stars formed in the last billion years, or two, represents a relatively small fraction of the total by number, though a larger fraction by luminosity, since young massive stars are disproportionately bright. The era of peak cosmic star formation, between about 2 and 5 billion years after the Big Bang, was also the era of peak quasar activity, when the most massive supermassive black holes were accreting material and producing the brightest active galactic nuclei in the universe. The coincidence of peak star formation and peak quasar activity is not accidental. Both trace the era when galaxies were most actively processing their gas reservoirs. The regulation of star formation by AGN feedback is one of the key processes connecting the growth of supermassive black holes to the evolution of their host galaxies. The standard stellar census counts stars that are actively generating energy through nuclear fusion. But the endpoints of stellar evolution, the white dwarfs, neutron stars, and stellar mass black holes that are the remnants of previously living stars, are also present throughout the galaxy and constitute a substantial fraction of the mass that was once in stars. Including or excluding these dead remnants changes the picture of what the galaxy's total stellar history looks like. White dwarfs are the remnants of stars that ended their lives with core masses below approximately 1.4 solar masses, a threshold called the Chandrasekhar limit. When such a star exhausts its nuclear fuel, the core collapses to a compact object, supported by electron degeneracy pressure rather than nuclear burning. The outer layers are ejected as a planetary nebula, and the remaining white dwarf has a mass typically around 0.6 solar masses and a radius approximately equal to Earth's. White dwarfs cool over billions to trillions of years, eventually fading to invisibility as they radiate away their stored heat. The Milky Way is estimated to contain roughly 10 billion white dwarfs. Most of these have cooled enough to be quite faint, and they contribute relatively little to the galaxy's total luminosity, but constitute a significant fraction of its total stellar mass. The local white dwarf sample within several hundred light-years has been characterized by Gaia, providing a basis for estimating the total white dwarf population. Neutron stars are the remnants of stars that were massive enough for their cores to exceed the Chandrasekhar limit at death, above roughly 8 to 10 solar masses during their main sequence lives. These objects are compressed to densities comparable to an atomic nucleus, with masses of 1 to 2 solar masses compressed into spheres roughly 10 to 12 kilometers in radius. Pulsars, a subset of neutron stars detectable through their beamed radio emission, provide the most direct window into the neutron star population. The Milky Way is estimated to contain perhaps 1 billion neutron stars. Stellar mass black holes, the remnants of the most massive stars above roughly 20 to 25 solar masses, are the hardest dead stars to find because they emit no light except when accreting material from a companion. The Milky Way is estimated to contain perhaps 10 million to 100 million stellar mass black holes, though this number is extremely uncertain. None of these dead stellar remnants are counted in the typical star census, yet they represent a significant record of stellar history. The universe has been forming and killing stars for over 13 billion years, and the accumulated population of dead remnants is in some sense the graveyard of cosmic history. The white dwarf cooling sequence has been used as a cosmic clock. Because white dwarfs cool at a rate that is relatively well understood from physics, the distribution of white dwarf temperatures in a population tells you how long the stellar population has been forming. The oldest white dwarfs in a globular cluster, those that have cooled the most, constrain the age of the cluster. By identifying the faint end of the white dwarf cooling sequence in nearby globular clusters and open clusters, astronomers can determine cluster ages independent of main sequence fitting, providing an important cross-check on stellar age estimates. Neutron stars and pulsars occupy a specific position in the stellar mass budget of the galaxy that is poorly known. Pulsars are detected through their beamed radio emission, which we happen to observe only when the beam sweeps across our line of sight, meaning that for every detected pulsar there are many more neutron stars that happen not to be oriented so that their beams point toward Earth. The beaming correction required to estimate the total neutron star population from the observed pulsar count is uncertain by a factor of several. The most massive neutron stars, those near the maximum neutron star mass of about 2 to 3 solar masses, may be the majority of the accreted or merged neutron stars that never appear as pulsars at all. Gravitational wave astronomy, inaugurated by the LIGO detection of a black hole binary merger in 2015, is beginning to provide a census of compact objects through their mergers. The rate of binary black hole mergers detected by LIGO and Virgo constrains the total number of stellar mass black holes in the universe, providing an independent estimate of the dead stellar population that will improve with increasing detector sensitivity and observation time. The boundary between the stellar and substellar realms creates a specific census complication that has only become tractable with recent surveys. Brown dwarfs, bodies with masses between roughly 13 and 80 Jupiter masses, are too light to sustain hydrogen fusion, but too heavy to be considered planets in any practical sense. Their existence as a numerous population in the galaxy was suspected theoretically, but difficult to confirm observationally because they are extraordinarily faint. Brown dwarfs cool as they age, unlike true stars, which settle onto the main sequence and maintain roughly constant luminosity for billions of years. A young brown dwarf has a surface temperature comparable to a cool star, perhaps 2000 to 2500 Kelvin, and emits detectable infrared radiation. But as it ages, it cools continuously, dropping through temperature sequences classified as L dwarfs, T dwarfs, and the coolest known objects called Y dwarfs, with surface temperatures below 500 Kelvin, cooler than some ovens on Earth. The significance of the brown dwarf problem for the stellar census is twofold. First, the population of brown dwarfs fills in the substellar regime just below the hydrogen burning limit, and understanding how smoothly the mass function continues across this boundary affects estimates of the number of stars at or near the fusion threshold. If the mass function rises steeply all the way to the brown dwarf regime and then drops sharply at the fusion limit, that is a different picture from one where the function peaks somewhere above the limit and declines on both sides. Second, brown dwarfs that formed alongside stars in the same molecular cloud collapse represent a population that has always existed alongside the stellar population, but has been chronically undercounted because they are so difficult to detect. The Wide Field Infrared Survey Explorer, WISE, launched in 2009, has been among the most productive instruments for finding brown dwarfs because of its sensitivity at the mid-infrared wavelengths at which cool brown dwarfs emit most of their light. It has found hundreds of new brown dwarfs, including some extremely cold Y dwarfs at distances of only a few light years from the Sun. The ratio of brown dwarfs to stars in the galaxy is not precisely known. Estimates from various surveys suggest there may be roughly as many brown dwarfs as stars, or perhaps somewhat fewer. If brown dwarfs number in the same ballpark as stars, they represent a significant population of substellar objects throughout the galaxy, though they do not contribute to the stellar count proper. The directly imaged exoplanet population and the brown dwarf population are increasingly being recognized as part of a continuous distribution of object masses extending from about a Jupiter mass up through the stellar regime. Some objects initially identified as brown dwarfs, orbiting stars, have been reclassified as massive planets based on their formation history, while some objects identified as free-floating planets have masses above the deuterium burning limit and are more properly called brown dwarfs. The boundary between these categories is blurry not only in terms of mass, but also in terms of formation mechanism. Two formation mechanisms can produce objects in the brown dwarf mass range. The stellar formation mechanism involves the gravitational collapse of a molecular cloud fragment that is simply too small to form a proper star. The planetary formation mechanism involves the growth of a solid core in a protoplanetary disk, followed by gas accretion, or alternatively direct gravitational instability in the disk. These mechanisms likely operate in different mass regimes and different environments, but the overlap region is not well characterized. Understanding whether the brown dwarf mass function is a smooth continuation of the stellar mass function or shows a distinct feature at the hydrogen burning limit matters for the stellar census because it constrains the amount of mass locked up in substellar objects throughout the galaxy. If brown dwarfs are as common as the faint tail of the stellar mass function predicts, they represent a significant reservoir of galactic mass that is neither stellar nor luminous in any conventional sense. The detection of brown dwarfs has been made possible by advances in infrared detector technology. Brown dwarfs emit primarily at wavelengths between 1 and 5 micrometers in the near and mid-infrared, where ground-based sky brightness from the thermal emission of Earth's atmosphere becomes a significant challenge. Space-based infrared missions, unaffected by atmospheric emission, have been essential for comprehensive brown dwarf surveys. The Spitzer Space Telescope, operating from 2003 to 2020, made major contributions to characterizing brown dwarf atmospheres and identifying new candidates in star-forming regions and in the field. After examining all of the methods, constraints, and uncertainties that go into the stellar census, it is time to state the actual number, or, more precisely, the range of numbers that current best estimates span, and the reasons for the remaining uncertainty. For the Milky Way, the most careful recent estimates place the total stellar count between approximately 100 billion and 400 billion stars, with a central estimate around 250 to 300 billion stars. The Gaia data have helped refine this estimate by providing accurate stellar counts in the solar neighborhood that serve as the foundation for galactic extrapolation. The wide range reflects genuine uncertainty in several parameters: the total mass of the galactic disk, the mass fraction in stars versus gas and dark matter, the stellar initial mass function particularly at low masses, and the correction factors for the unobserved stellar population behind dust. Within the solar neighborhood, defined as the region within 100 parsecs of the Sun, the census is more complete. Approximately 260,000 stars are currently catalogued within this volume, and corrections for incompleteness at the faint end suggest the true number within 100 parsecs is somewhat higher, perhaps 300,000 to 350,000 stars. The local stellar density works out to roughly 0.004 to 0.005 stars per cubic light year on average. For the observable universe, the most cited estimate of the total stellar population comes from a 2003 study by Simon Driver and colleagues, updated by subsequent analyses, which arrived at approximately 7 times 10 to the 22nd stars, or 70 sextillion. Other estimates span from roughly 2 times 10 to the 23rd to 10 times 10 to the 23rd, a factor of roughly 5. The uncertainty comes predominantly from the galaxy count, the mass-to-light conversion for different galaxy types, the IMOF assumptions for massive elliptical galaxies, and the dust correction in star-forming galaxies. The number 10 to the 24th is sometimes cited as a round number to use for the total stellar count in the observable universe. This corresponds to roughly 1 million billion stars, or equivalently about 100,000 stars, for every grain of sand on all Earth's beaches combined. These numbers are best current estimates, not measurements in the direct sense, and they will be revised as future surveys improve the completeness of the local stellar census. As better models of stellar populations reduce the systematic uncertainties in the moss-to-light conversion, and as more sensitive infrared surveys detect the faintest red dwarfs and probe more completely the low-mass end of the stellar mass function. A useful way to cross-check the integrated light approach to counting stars in the universe is to compare the inferred stellar mass density to the density expected from the cosmic star formation history. If you integrate the cosmic star formation rate density over all of cosmic time and account for the mass returned to the interstellar medium when stars die, you should get the current stellar mass density. Agreement between these two approaches, one based on the observed properties of today's stellar populations, and one based on the history of star formation, provides confidence that the estimates are roughly consistent. Such comparisons have been made and generally show acceptable agreement within the uncertainties, though there are discrepancies at the level of a factor of 2 in some cosmic epochs that are subjects of ongoing investigation. These discrepancies may reflect systematic errors in how star formation rates are measured at high redshift, or they may indicate that the conversion factors from observed galaxy light to star formation rate carry systematic errors that accumulate over cosmic time. The revision of the galaxy count from 100 billion to 2 trillion in 2016 has not yet been fully propagated through all stellar census estimates. Some widely cited figures for the total stellar count still use the older galaxy count as their starting point, making them potentially underestimates by a factor of up to 20. The stellar census is an actively evolving research area, and figures quoted in review articles from even a decade ago may be outdated in specific ways. The most reliable current practice is to cite a range and to be explicit about what assumptions and data go into the estimate. The number itself, 10 to the 23rd to 10 to the 24th stars, is in some sense too large to be meaningful. Human intuition developed to handle quantities from 0 to perhaps millions, and even billions and trillions require a specific act of conceptual effort to appreciate. A number with 23 or 24 zeros is genuinely beyond any intuitive grasp, and attempting to develop intuition for it is probably less productive than understanding what it implies about the universe. What it implies is scale. The observable universe is not marginally larger than any individual collection of objects we can directly comprehend. It is larger by a factor that exceeds any reference point in ordinary experience. The most productive way to understand the stellar count is not as a number, but as a constraint on what the universe is like in terms of its capacity for generating complex chemistry and, potentially, complex phenomena. Stars are the factories of the universe. They synthesize essentially every element heavier than hydrogen and helium. The carbon in organic chemistry, the oxygen in water, the iron in blood, the silicon in rock. All of these were produced inside stars and expelled when those stars died. The stellar population of the universe is therefore the chemical factory that made the material, complexity from which planets, oceans, and biology have emerged. A universe with 10 to the 23rd stars has produced an amount of carbon, oxygen, and other biologically relevant elements so enormous that the mass of all living things on Earth is a negligible fraction of the available substrate. The stellar count also constrains arguments about the probability of life. If the probability of a habitable planet forming around any given star is small, even an extremely small number, the product of that probability and 10 to the 23rd still produces an enormous number of potentially habitable planets. The stellar census, by establishing just how many stars there are, makes certain kinds of arguments about the inevitability or rarity of life more quantitative and more testable. The uncertainty in the stellar count also has a message of its own. We do not know to better than a factor of 3 to 5 how many stars exist in the observable universe. For the most fundamental census of the most abundant object in the cosmos, this precision is genuinely the state of the art. It reflects how difficult the problem is, how many layers of inference are required, and how much of the universe remains inaccessible to direct observation, either because it is hidden by dust, or because it is too distant to resolve, or because the objects of interest are too faint to detect. The comparison between the number of stars and the number of atoms in specific objects helps calibrate the scale of the stellar count intuitively. A grain of sand contains roughly 10 to the 18th atoms. The human body contains roughly 7 times 10 to the 27 atoms. The number of stars in the observable universe, 10 to the 23 or 24, is roughly comparable to the number of atoms in a few teaspoons of water. Not comparable by coincidence, but comparable as a coincidence of scale. It happens to be that the large natural number of atoms in a small amount of matter sits in the same numerical range as the large natural number of stars in the observable universe. The philosophical implications of the stellar count connect directly to the question of cosmic significance. If the observable universe contains roughly 10 to the 23rd stars, and if the distribution of stars throughout space is broadly similar everywhere in the observable universe, then there are roughly as many stars in the observable universe as there are atoms in a few tablespoons of water. The human intuition that individual things matter is calibrated to a scale where things can be counted. The stellar count confronts that intuition with a scale at which individual things are statistically negligible. This statistical negligibility does not, of course, imply meaninglessness. The specific arrangement of matter in any particular location, the presence of a specific star, the specific planetary system around it, the specific chemical and biological history that produced an observer capable of asking how many stars there are, is as specific and as unlikely as any other arrangement of the same matter. The vastness of the stellar count is the context within which that specificity becomes remarkable rather than expected. The question of how many stars there are is a modern question. Ancient and medieval astronomers were not asking it, not because the question didn't occur to them, but because nothing in their observational or theoretical framework gave them any reason to think the answer could be anything other than a few thousand. The idea that the universe contains structures larger than the solar neighborhood, structures containing billions of stars beyond any that the eye or the early telescope could see, is a product of the last few centuries of scientific progress. The progression from Hipparchus's 850-star catalogue to the Gaia satellite's 1.5 billion star astrometric database to the estimated 10 to the 23rd or 24 total stars in the observable universe is not merely a story of accumulating more data. It is a story of conceptual expansion, of the human understanding of the universe's scale increasing by many orders of magnitude in a relatively short time. Each time the scale expanded, it did so by revealing that what had seemed like the limits of the universe were actually just the limits of current instruments or methods. The current best estimate is probably not the final answer. Future surveys, particularly space-based infrared missions designed to detect the faintest red dwarfs and the coldest brown dwarfs in the solar neighborhood, will refine the local stellar census and reduce the dominant source of uncertainty in the galactic stellar count. The James Webb Space Telescope, operating in the infrared, is probing stellar populations in nearby galaxies with unprecedented detail and is beginning to constrain the stellar initial mass function in environments very different from the solar neighborhood. The Nancy Grace Roman Space Telescope, when it launches, will conduct wide-field infrared surveys that will detect billions of stars in the Milky Way and its neighbors. The number will be revised. It may go up if the initial mass function turns out to be more bottom-heavy and massive galaxies than currently assumed, meaning more low-mass stars per unit of galactic stellar mass. It may go down if improved surveys in the local neighborhood revise the faint end of the luminosity function downward, but the order of magnitude, the rough class of the answer, is unlikely to change. We live in a universe that contains somewhere between 10 to the 22nd and 10 to the 25 stars, and the number we currently use as our best estimate sits in the middle of that range. Somewhere in that vast inventory, the Sun is one star among a few 100 billion in the Milky Way. It is not particularly massive, not particularly bright, not particularly old. It sits in a typical location, in a typical galaxy, in a typical part of the universe. What makes it interesting is not any special astronomical property. It is what formed around it, and what evolved on one of the objects that formed around it. The counting of stars that astronomers have spent centuries constructing is ultimately counting the context in which that particular story, the story of chemistry complexifying into biology and eventually into minds that can ask how many stars there are, became possible. The counting is not separate from what is being counted. It is part of the same story. The methods astronomers use to count stars are themselves a kind of astronomy, a meta-astronomy that studies not the objects themselves, but the population of objects and the statistical distribution of their properties. The luminosity function, the initial mass function, the stellar population synthesis models, the dust extinction maps. These are the tools of the demographic approach to the universe. They treat the stellar population the way ecologists treat animal populations, or epidemiologists treat disease distributions, as statistical phenomena to be characterized by their distributions, rather than their individual members. This demographic approach is not limited to stars. The same methods are applied to galaxies, to galaxy clusters, to dark matter halos, and to the large-scale distribution of matter in the universe. Astronomy at the largest scales is fundamentally statistical, because the scales involved are too large for individual characterization of everything present. The census of stars is a specific instance of the broader project of characterizing what the universe contains and how it is distributed. The act of counting stars, or approximating a count, also has a history that connects to the broader history of human attempts to understand the universe's scale. From the few thousand visible stars of ancient catalogues to the billions of Gaia to the sextillions of the full universe, the count has grown by many orders of magnitude as new tools and new frameworks became available. Each expansion of the count required not just better instruments, but better conceptual frameworks. Understanding that the Sun was a star, that the Milky Way was an aggregate of billions of stars, that there were billions of galaxies, that there were 2 trillion of them rather than 100 billion. The count is inseparable from the understanding that makes the count possible. What remains unknown is whether the next expansion of the stellar count will require yet another conceptual revision, whether the observable universe itself is only a small fraction of a larger cosmos, whether the 2 trillion galaxies we see are a tiny sample of a much vaster ensemble, and whether the number of stars we have so painstakingly assembled represents something close to the full cosmic total, or yet another radical underestimate waiting to be corrected by the next generation of observations and ideas.